Maybe, maybe not. Does it mean that it's deep bubble flow? Not yet. Okay. Step 1, we can check just whether it's stratified or not. Okay. If it is not stratified flow, we check transient B. Okay. Transient B is to check if it is annular flow or not. So when the point is over there, this point is outside the transition B, right? Transition B is the plot between H tilde, just that H tilde equal to 0.35. H tilde is small h over d on scale liquid height and pi. So that point has H tilde more than 0.35. So that point is not annular flow either. Okay. So let's go back. Next step we check. Okay. We skip this part because transient C is for the case where it is stratified flow. We check capital D. Capital D is to check whether it is dispersible flow or intermittent flow. That is capital D. Look at this carefully. Capital D, so we do A, B, and then D, okay? So capital D is a plot of T versus H tilde, okay? We check capital C only for the case where it is stratified flow. Capital C will tell us, transition C will tell us if it is stratified smooth or stratified wavy. But since we know that this case is not stratified to begin with, so we can skip, we have to skip transition C, okay? So it's A, B, and then D. So transition D is not the plot of F versus H, it's T versus H, okay? So T versus H. Even though F versus H is over there, but T, okay, you see the value of T. The value of T can be something else. Because what? T is from other expression. You see that the equation for capital T is something else. So the value for T doesn't need to be the same as the value of F. So even though F is over here, H tilde is over here, T may be over there. So T can be over there and it could be this bubble flow. Or T can be over here, or T can be over there and it's intermittent flow. So when we check transient, when we calculate the value of T is to check transient D. Transient D will tell us whether it's this bubble flow or intermittent flow. Question, I think it's a little bit confusion. Question for me.
Will T be given?
Will be given. T will be given. And the time required for me to prepare the exam is quite a while, but you just, okay, F equal to this, T equal to that, K equal to that, then you get this graph and you check what is what. Very quick, right?
We have like an example of this, like a practical example.
It's on the old exam with the solution, okay? But without any example, I think it's easy enough. We check step 1, check the transition A to check if it is stratified or not stratified flow. If it is not stratified flow, we check transition B. Transition B is based on H tilde of 0.35. So if H tilde is more than this, then it's not annular flow. If it's less than this, then it's annular flow. Okay, that is step 2. If it is not annular flow, then we check transition D. Transition D is a plot of capital T versus H tilde or HL over D. So if T is below that line, then it's intermittent flow. If it is above, then it's dispersible flow. Good? Alright. What about that capital K? Where do we use it? Yes, sir.
So the flow can be like stratified, annular, intermittent, right? So we have to check like between.
Step 1, check whether it's stratified flow or not. If it is not stratified flow, we check this line, whether it's annular flow or not.
If it is stratified stratified?
If it is stratified flow, we don't check that. We don't check that. If it is stratified flow, we check transition C. Okay, transition C is plot between capital K and H tilde or H over D. So if it is stratified flow, we want to know if it is stratified smooth or stratified wavy. In that case, we check K value. K value, this is the formula for K value. I will pre-calculate it. Okay? Because look at this formula. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. When you put this, use a calculator, it's very likely to get it wrong. Okay? Yes, ma'am?
Can we use those same equations if the liquid flow is both oil and water?
Oil and
Water?
oh, you wonder if we have this kind of chart for oil and water or not, right? There is. We don't teach it at all.
One of the homework questions is
For oil and water, the chart is pre-calculated in dimensional format. Okay, this one. You see this one? This chart is dimensional format. Is superficial velocity versus superficial velocity of oil and superficial velocity of water. So this chart is specific for that kind of fluid property, that pipe geometry. So you can use it right away. Just have to calculate VSW and VSO, then we do this. Okay.
and what do we use for those?
What we are talking about over here, so this case, the dot that you see here is the model prediction, right? The dot that you see here is the flow pattern prediction. The case that we're talking about here is how do we predict the flow pattern? If the flow pattern is already predicted, and you want to know if we have this much water flow rate, this much oil flow rate, what is the flow pattern? That is easy because the flow pattern map is already generated. This chart is used to generate the flow pattern map. When we use this chart when we do not have this chart. Okay? If we don't have this chart, we don't know where is superficial wavy, where is whisper bubble flow, where is annular flow. We don't have any of this. We don't have any of this. How do we know when we have one point in space? I don't use the program generators. By the way, this is work for water. Option 1 that I have is use the program to generate for the case of oil and gas that I have. Option 2, then I will get this map. Okay, I will get this map. Option 2, I do this. This will tell me what is flow pattern. Like this is a manual, that one is from computer. Good. And you will know how to use both. Okay. Manual way is used to generate the curve in that computer program. So computer program, okay, this is computer program plus experimental result. So the line, the dash line, is a computer program line. Okay, this dash line is from computer program line. So basically, the way that it works is we select one point, we use that chart, like the flow pattern chart, this kind of chart, and we find out what is the flow pattern and we move on. We do every point that we can tell how does the flow pattern map look like. So that kind of flow pattern map, we get it. Either we do experiment or we use computer to generate it. But if we don't do experiment, okay, because we cannot, like, okay, 6 inch and a certain oil viscosity, certain oil density, we cannot buy that oil and do the experiment. This is how we predict it, okay? So this is how we predict it. We assume, we calculate the value of x, value of y, get h tilde, use this chart. then we can tell what is the flow pattern. This is good for horizontal and plus minus 10, horizontal and horizontal. So if it is not stratified flow, meaning that when we use transition N is below. So when we plot F versus H tilde is below. Then we look at the value of K, check the transition C. And we check the transition C with the value of K to see if it's inside over here or it's outside. If it is outside, it's stratified wavy. If it's inside, it's stratified smooth. More question, please. Question. Yes.
For the homework, you gave us a question with the oil viscosity, water viscosity, oil and water flow rates, and we're trying to find the outlet pressure. How do we calculate the pressure drop given those two different?
Do we assume pseudo single phase? Do I tell you flow pattern, or we tell that it's a well mix? I don't tell anything. How do you estimate anything?
You just say it's an emulsion.
Yeah.
Emulsion.
And
Emulsion means it's well mixed. Okay. Whenever it's emulsion, it's very difficult to break emulsion. When it is emulsion, the keyword emulsion means it is either that or that. Did I say oil in water or water in oil?
Water.
Water in oil or oil in water?
water and oil.
Water in oil. So water in oil is this one. So whenever it is emulsion flow like that, like in the homework, we use pseudo single phase approach, and it will be absolutely correct. There is no slip. We do everything like single phase flow. We calculate emulsion viscosity by use this equation. Okay. Brinkman equation is to calculate emulsion viscosity. Use weighted average based on hole up, then you calculate the density. Did I give you hole up? Or I did not? Hole up equal to no slip hole up. No slip hole up is VSL over VM. VSL, or you can say hole up of oil phase or hole up of water phase. Okay. Lambda water equal to flow rate of water over flow rate of water plus flow rate of oil. So that lambda is that. So this is pseudo single phase approach. Good? Can you calculate lambda? Yes. Lambda comes from this equation. Okay? Q over total Q. So if you want to know the lambda of, so it's water in oil, right? Water is dispersed phase. So lambda of water, this is Q water over total Q, or flow rate of water divided by total flow rate. Then we can calculate, okay, continuous phase will be oil, so that will be mu O, right? Mu O. Hole up of the dispersed phase will be lambda water, L sub W. Okay, then we can calculate mixture viscosity. Good. We can also do weighted average to get mixture density. Okay. So Marty, you following this? Good. All right. So we calculate mixture density, mixture viscosity. Next step is calculate Reynolds number. If Reynolds number, I think that case is less than 2100. So Reynolds number less than 2100, we use 16 over Reynolds number to get friction factor. If it is more than that, we use Harlan equation. Okay. So when we get friction factor, we do 2F over V squared over D. Yes, ma'am?
The slide says that lambda is equal to Q liquid over Q liquid plus Q
Gas. That is for the case of gas liquid flow. For liquid flow, we change that to water, oil, and this will be lambda water. So basically it's like fractions, how much is a fraction of water. So this will tell lambda is estimated value of the fraction of water.
But when we're given gas also, then we just do it like that.
So this slide is about liquid. So that HW is this HW equal to lambda W equal to Q of water divided by Q of water plus Q of oil. Q is the flow rate. We don't have gas anymore because this is the oil water flow. Okay. Question? More question. The solution will be posted next day after you select your choice. Whatever you select, you get 10. If you don't select that question, you get 0. Okay? Try to select something. Okay. So this is the way this is a no-slip model. Assume everything well mixed. The way that we mix is, to calculate the fluid property is weighted average based on the volume fraction. Volume fraction is based on the flow rate fraction. If I have gas, oil, water, everything flow together, we get fraction of each phase. Okay, and then we do density weighted average of fraction of each phase. Okay, for the viscosity, we have to mix oil with water first, and then to mix emulsion with gas, we do this. We don't have that in the exam, it's too difficult, okay? But that's if you want to, there's always a way to calculate. The exam, if you do that question in the homework, okay, or if you follow the solution of that, you should be fine for the exam. More question? Okay. Alright, this is the way we do flow pattern for horizontal and near horizontal. It's not for every angle. It cannot be used for vertical flow. Okay. So in the vertical flow, we have easier version. Okay. This is just to check if it is annular flow or not annular flow. Sometimes the prediction from this graph is not the same as the prediction from this graph. Okay. So the prediction from annular or not annular from this chart is not the same as this chart. We go by this one because this is the model that is the more updated version. This chart is so easy. Once you get the value of x and y, you find out where is that value. So if it is in this region, okay, this annular flow. If it is outside, over here or over there, it's not annular flow. This is a quick check to see if we should have annular flow inside the well or not. Okay. If we have annular flow inside the well, this means it's for sure we don't have liquid loading problem. Okay. This means for sure we don't have liquid loading problem at that point. Okay. This is a lot better than the Turner equation. Okay, Turner equation, just the force balance. This one is a little bit like more complicated. So calculate x and y. Use this chart. We can tell if it is annular flow or not. Any angle, including downward flow. Okay, including downward flow. 90 degree downward, 45 degree downward, horizontal, upward, perfect upward. It works for all. Okay.
Does the other one allow for downward flow? Is it the plus minus 10?
This is just plus minus 10. Also these two. This is also plus minus 10. This is not even plus minus 10. This has to be perfect horizontal. Okay, this has to be perfect horizontal. So by doing this, we get flow pattern. Why do we want to learn anything about this in the facility? Where do we have multiphase flow inside the facility? After the separator, everything kind of separate, right? We don't have any of this. But before it reaches the facility, from the wellhead to the first separator, it will have multiphase flow. Inside the well, this thing apply. Okay. In the subsea pipeline, this thing apply. Subsea pipeline has horizontal section and vertical section before it reaches the platform or before it reaches the first separator. This calculation apply. Okay. All right. And this is the definition of each parameter. This is flow pattern calculation. Good. The flow pattern prediction is just step 1. Once we know the flow pattern, step 2 is to get pressure drop. Do I test you how to do pressure drop? Not really, it's too difficult. It's become extremely difficult. But we will take a look at it so that you understand the software that you are using, where does it come from? Okay, what is inside? Okay, do you want to know or anyone tell me any number, I just try it. Okay, inside the software to calculate the pressure drop, number 1, there has to be some assumption of the fluid distribution inside. So in this case, they assume a flat interface, not a curved interface. Is this true? Do we have the flat interface? Only for the stratified flow case. When we flow gas a lot, this water or this liquid can climb up and have a curved interface. Okay. Inside the software, they have geometric relationship. Like, okay, let me continue. Okay, we have geometric relationship, and to calculate pressure drop for stratified flow, okay, they use combined momentum equation. Okay, from the combined momentum equation, once we know the height, okay, we know the liquid height. Liquid height is come from this chart. So this chart, if the flow pattern is stratified flow, this chart will be the true height. If it is not stratified flow, this height doesn't mean much. Okay. If it is stratified flow, we have that height. We use the geometric relationship. We calculate every area, everything. Then we calculate other related parameters. Plug it back in. You try to kind of understand why I cannot test you on that because it's too long. It's very long. So basically, you calculate actual velocity. From the actual velocity, we calculate shear stress. Put shear stress into one of these equations, then we get pressure drop. Okay, this is for steady state pressure drop calculated for stratified flow case. We don't have just stratified flow. Sometimes we have slug flow. Slug flow is a combination of dispersible bubble flow and stratified flow over here. Okay, and this film it can flow backward, right? Okay. Okay, what can be in the exam? The only thing that can be in the exam in this is this relationship. Okay, this is what you need for the exam. It may not be in the exam, but if it is, it's just that. Translational velocity is the velocity of the interface is even faster than VGTB. VGTB is a gas inside the tiller bubble. Gas inside the tiller bubble is faster than gas inside the liquid slug. LS is liquid slug. So we have gas over there and gas over there. Gas in tiller bubble is faster than gas inside liquid slug. We have VLRS, which is liquid inside liquid slug. And we have VLTB, liquid in the liquid film. Liquid in the liquid film is slowest. Okay? If you have this, and you review it, that's it. The rest, this is the explanation on what is going on inside steady state software. So in the steady state software, they calculate pressure drop based on density of the slug unit, film length, okay, length of the film, length of the slug. Okay, it needs the shear stress. To calculate shear stress, we need to know the actual velocity. Once they know all that, they plug everything in this equation and get pressure drop. Okay. So what is that telling me? Which parameter is important in this case? Okay, which parameter? What do you think? I think this rho is very important. And because for horizontal flow, sin theta is 0, right? We don't have any gravitational term, so that thing is gone. It depends on the film length. Okay, it depends on the film length. But for vertical flow, this term is the dominating factor. The rest doesn't matter much. Okay. So this is combination between hydrostatic head and friction term. Hydrostatic head is dependent upon hold up, the total hold up of the slug unit. Okay. Conceptually, you kind of understand that the pressure drop prediction that you get from the simulator is not just come off nowhere. Okay, there is a way to calculate, but it's really difficult to test you because it's too long. I actually test a grad student, but I use a calculator to do that. Okay, but we don't have this in here. Right, there is slug flow. For slug flow, the calculation is a little bit lengthy. Okay, we have another flow, another lengthy calculation. What I try to show here is we skip everything, okay? But what I want you to know is that this kind of calculation is based on the combined momentum equation, okay? Or at least the momentum equation of each phase. Once every parameter in that equation is known, then they can calculate pressure drop, okay? So this is a detail. What happened is, step number one when the simulator work is calculate the flow pattern. Okay. Predict the flow pattern is the number one objective. After we know what kind of flow pattern that we have, then we predict the pressure drop accordingly. If it is stratified flow, we use stratified flow momentum equation to predict the pressure drop. If it is slug flow, we use slug flow momentum equation to predict pressure drop. If it is annular flow, we use annular flow momentum equation to predict pressure drop. One thing that you may want to know is, inside those pressure drop predictions, there's always something that math cannot predict, and it has to come from measurement. For example, annular flow requires this kind of closure relationship. Okay, we don't go into detail, but this is about how much is the entrainment fraction, how much is the liquid droplet inside. Okay, mass flow rate of the droplet versus total liquid flow rate, how much is that? This kind of thing is from closure relationship, come from measurement. Okay, so this means inside the mechanistic model we still have some empirical part. Okay, for slug flow, something comes from closure relationship. For example, in slug flow model, VTB, which is the translational velocity, comes from closure relationship. Okay, what else is come from closure relationship? Hold up of the slug unit come from a closure relationship. Okay, L sub S come from closure relationship. Okay, so L sub S is the length of the slug unit. For stratified flow, friction factor at the interface, okay, H sub I come from closure relationship. So what I try to tell you is, in each pressure drop prediction, okay, even if it is a mechanistic model, there are some parameters that cannot be predicted, and it has to come from closure relationship. A closure relationship is validated against a certain data set. Okay, it may be 6-inch pipe. If you want to extrapolate the model, this means we extrapolate the use of the closure relationship inside mechanistic model. So that's why it could be wrong too. Okay. So this is, in conclusion, we learned about flow pattern, how does it look like, and we learned that mechanistic model is more accurate than pure empirical model. Okay, and you know how to read the graph, capital F, capital T, okay, H tilde, that thing. The shot will be given, yes sir.
Sir, are you saying closure relationship? I can't understand.
Closure relationship is maybe
You got closure?
is an empirical equation that used in, is a curve fitting equation. Yes.
Can you spell it out? Yeah.
Closure, C-L-O-S-U-R-E, closure. relationship, that is closure relationship. It's empirical correlation in the model that they use to predict something that the model cannot capture.
You said mechanistic model is better than the empirical.
Mechanistic model is better than empirical model. Yes. Okay, we don't go anywhere yet. Okay, we have 10 minutes and some of you gonna. Okay. Next is about. We skip from assurance for now and let's talk about the thing that is in the homework, which is a heat transfer. Is it? Okay, heat transfer. In this heat transfer, we have one important equation, okay, that I want you to write down, which is that equation. It is an equation to predict the temperature at any location. Okay, it predicts the temperature of the fluid in the pipe at any location, provided that we know overall heat transfer coefficient. Okay, we know mass flow rate, we know specific heat capacity, and we know length from the inlet. Okay. In addition to that, we know environment temperature. Okay. Then I can predict the temperature. That's it. Okay. This part is related, okay, to the facility in the sense that if we want to know, if we really want to predict the temperature of pipe that is not varied, if the pipe stay underground, how much is the temperature is the liquid travel by 1 mile. If the pipe above the ground, we have a certain wind speed, when it reaches the facility, what will be the temperature? If we have the buried pipe, this thing actually can calculate too, okay? So this is one equation. And it can be used for subsea pipeline, okay, to, when we look at this equation, capital U is overall heat transfer coefficient, okay, that is capital U, quite long to do that calculation, okay, this is quite long. T infinity is environment temperature. T at any Z is the temperature at any location that we try to predict. T inlet is the inlet temperature, okay. So this means if we know the inlet temperature, we know the environment temperature, then we can do the calculation. In the homework, it's not quite a homework, it's actually like a tutorial for the last question, okay? When you follow the calculation, at the end, we just substitute the value in and we get the temperature. So if I have a pipe above the ground, we have wind at 20 miles per hour blow across it, okay? We have to do something to get U value, okay? Once we have the U value, we know the mass flow rate of liquid inside the pipe, okay? Specific heat capacity of that oil. Then we substitute the value of Z is the length from the inlet. Then we can calculate temperature at that location, okay? This equation, if we put Z equal to 1, it will tell temperature at 1 meter away from the inlet. If we put Z equal to 10, it will tell the temperature at 10 meters away from the inlet. So when I have Excel sheet, column 1 is the distance and have many numbers. Column 2, plug this equation in, we have temperature at every location. So it can be done like that, okay? The difficult step is to calculate U value. M dot is given, liquid mass flow rate. Okay, by the way, this equation should not be used for gas flow. It is valid, but by itself it's not complete. Okay, it's valid, but it's not complete. The reason that I'm saying that is, it doesn't include Joule-Thomson effect, right? It's no Joule-Thomson, it's no like cooling due to pressure drop. This equation doesn't say any of that, okay? It doesn't really take it into account the change of the fluid property versus temperature. If the viscosity change, Will this equation work? Not really. So it still works if we divide the pipe. Okay, we have the pipe very long. We divide the pipe into several sections. And we know that, okay, this section viscosity equal to 10 centipoint. This section is maybe 20 centipoint, 30 centipoint. So then it can work, okay? The rest, try to follow whatever in the homework, okay? The homework is kind of tutorial. So in the last 5 minutes, let's take a look at something, okay? Mass flow rate is given, okay? Look at U value. U value must be referenced at a certain radius, okay? Sometimes it is referenced at the inner radius or inner diameter. Sometimes it is referenced at the outer diameter or the outer radius. It has to be clear. When someone tells you the U value is not complete yet, he or she has to tell you that U value is referenced at what diameter or at what radius. For example, in this case, I give the whole expression of U value. In this case, U value is multiplied by R sub I or inner radius. So this means this U value is referenced at inner radius. Okay. Sometimes they may give you 1 over U and R sub O. So in that case, that U value is referenced at outer radius. Whatever it is, let's go back. You see that U multiplied by D. That D, if that D is the inner pipe diameter, that U has to be referenced at the inner pipe diameter. If we use that D for the outside diameter, that U has to be referenced at the outside diameter too. Basically, U multiplied by D in this equation is equal to 2URI, or you do this minus 1 and multiply by 2. So this whole term, just this part, is that you multiply by D, okay? Next time, we will go over this a little bit more. We still have 3 more minutes, and but by now, you should be able to do the homework already. The rest, let's do this U value calculation. Okay, don't go anywhere. Don't go anywhere. U value calculation. U value is overall heat transfer coefficient. So this means we add several layers together. When you see this picture, this part is the heat transfer due to K12, or thermal conductivity from the red portion. So the part that has K value is the part about conduction through solid. Okay, conduction through solid. The place where it have H, and H over there, this is convection, through fluid when we have the flow. Okay, so the way that heat transfer is heat from the inside. Let's say our pipe is hot, liquid inside is hot, and environment is cold. Heat from the inside travel from the center to R1 by convective heat transfer. So that is that term. Then it conduct, due to the conduction, it goes through from R1 to R2. So this is the conduction in that layer of the pipe. Then it have another conduction to go from R2 to R3, another conduction to R3 to R4. When the heat is outside, it transfers to the environment due to convection. This is that term. Okay. These 3 terms is kind of easy to calculate because you just need to know the geometry. How much is the insulation layer thickness? That will tell, right? Let's say R3 is outer radius, R3 is inner radius, R4 is outer radius. We can feel this. K value is a solid property. Those are easy. But the thing that is not easy is this HI and HO. Okay. HI and HO is not fluid property. It is the flow property. When we flow fast, H value go up. When we flow slow, H value go down. So it is a flow property. So there's a quite lengthy formula to calculate H, and that's H, to be able to get that U value that we plugged in back in here. Okay, thank you for coming. We'll see you again next time. That will be the last time. We will talk about heat transfer and a little bit on quadrants. Please try the homework, and optionally, we may have